Now we know what is a spectral representation, and now we want to use the relationship we talked about and then solve the problem. So what we know is that if you give the innovation process to the LTI filter with impulse response of, let's say, gamma of t, then you get if you give x of t, you give it to the whitening filter, it gives you I of t. It gives you the innovation process. So the innovation process is just a convolution of the impulse response of the whitening filter and the input. Now, so we also know that the power spectral density of input should be this one, and then from here you get S I of omega shall be equal to 1. So it's a flat power spectral density. So because it's white. So if you write it in Laplace domain, it should be equal to 1. And also we have x of t is equal to convolution of this is the filter, so it's kind of in a way, so it's the inverse of that filter, it produces that. So from here you get x of s is equal to L of s, and then L conjugate of s conjugate times x SII of s. SII of s. So which is, you see that the power spectrum of x is equal to L of s. So you could write this relationship for autocorrelation function. You get this relationship, and what we know is that both filters, innovation and whitening filter, they should be stable, and also they should be causal. So the causality is required when you work with time, like for when you do for image, causality is not required, but the stability is required all the time. So causality and stability together are so, and then these filters, they should be also invertible, because using x of t you produce I of t, and you should be able to reproduce x of t to get it back. Otherwise this is not going to be a representation. So these three properties, stability, causality, stability and invertibility is always required. Causality is needed when you are implementing time. Sometimes we could avoid causality by accepting some delays. A spectral representation, so we want to use those things. So in the Laplace domain, we concluded, because if you multiply these by SII of s, and this is 1, okay? So if your filter coefficients are complex, then you need to put a conjugate here and here. But if all parameters are real, you don't need to put it there. For digital domain, instead of S, you work in Z domain. So in that case, you say x of Z is equal to L of Z, and then you will get L conjugate of, instead of minus S, you get 1 over Z conjugate. And if parameters are real, you don't need to put any conjugation. So this problem is just a decomposition. If the power spectrum of the input random process is given to you is a function, then the problem comes to find, so is given. The problem is find L of s. And this problem is not difficult, because it's just a function, decompose it into to its terms. So this problem is known as power spectrum factorization of x of t. So it's kind of like decomposition of these is power spectral factorization of x of t. So this is the term we use. So you could replace s by j omega, and this is becoming equal to this expression. So it is easier to work in S domain because you can get the roots, poles, and so on. So if this is given to you, usually you replace S equal j omega. So, or you replace omega by the minus js or whatever is that. So you usually replace, if your function is a function of omega 2, you replace S2 is equal to minus omega 2. So you replace this by that. And then you get this function, and then you go from there. So a spectral representation, we will solve several problems. In summary is that if the power spectrum is given to you, we want to find a minimum phase analytic function Ls such that this function, this equation is satisfied. Now, we will define what is a minimum phase analytic function. Minimum phase analytic function means that this filter is causal, stable, and implementable. There is a theorem which we will not prove it. This theorem says that for any power spectrum which satisfies this function, which is called Paley-Wiener condition, the spectral representation has a solution, or a spectral factorization has a solution.